To find the inverse of f of x equals 2x plus 7, I'm going to rewrite the equation as y equals 2x plus 7, and then my inverse is x is equal to 2y plus 7, so switching the x's and the y's. After I subtract 7 and divide both sides by 2, I arrive at my final answer because I have y by itself. The expression over here has no y's in it. Therefore, my answer is x minus 7 over 2. For g of x, again, y is equal to 10 minus x is just re-expressing the function to then write the inverse as x is equal to 10 minus y. So I think for this one, I'm going to add y to both sides. And then I'm going to subtract x from both sides. And this is my answer, 10 minus x. In question 3, this equation is already set up as y is equal to, and I'm going to write my inverse as y to the negative 1. In this context, there's no confusion since I'm asking to solve for the inverse. I do not mean 1 over y. Anyways, the inverse equation is x is equal to 2/3 y plus 4. I'll subtract 4 from both sides, and now I have that is equal to 2/3 y. What I'm going to do next is multiply both sides by the reciprocal, which is 3/2. This will cancel the 2/3 and leave me with 3/2 times x minus 4. You could, of course, distribute that 3/2 into the expression, but my final answer is simply 3/2 times x minus 4. There's a slight typo here in question 4. I called my function k of t, but I left the variable as x. I'm replacing it with a t here. That is exactly what I meant originally. But anyway, again, this is y is equal to, I'll use 5t plus 6 over 7. Therefore, my inverse is t is equal to 5y plus 6 over 7. I'll first multiply both sides by 7. Subtract 6 from both sides. And divide both sides by 5, and I arrive at my answer. Y is equal to 17 minus 6 over 5. And writing that up here, I'll just put 7t minus 6 over 5. Questions 5 and 6 are closely related, so for this problem, I'm actually not going to switch around f and c or relabel anything. I'm simply just going to solve this equation for c just to see what happens. So to do that, I would start by subtracting 32 from both sides. And to get c by itself, I'd have to multiply both sides by 5/9. And on the left side, I have 5/9 times f minus 32, and that is equal to c. And this is precisely the equation that is present in question 6. c is equal to 5/9 times f minus 32. So for this problem, I chose to leave everything in terms of f and c, not put f inverse over here or c inverse over here. The thing to notice is, if you take this equation and find its inverse, it takes you to this equation, and vice versa, if you find the inverse of this equation, it'll take you back to this one. I'll just make a note that these two equations are inverses of one another. This fact is true for any equation. If you find its inverse, if you then took that brand new function and found its inverse, it would take you back to where you start. Going back to our standard notation, I'm going to call this y is equal to x cubed plus 4. My inverse will be x is equal to y cubed plus 4. I'll start by subtracting 4 from both sides. And to get y by itself, I have to use some type of root, and that root would be the cube root of both sides. Cubing a cube root, or said another way, cube rooting a cube would just give you y. And on the left side of my equation, I have the cube root of x minus 4. That is exactly what the inverse of h is equal to. All right, so again, since I'm starting with y is equal to, I'm using this y to the negative 1 to mean the inverse of this function. The inverse is technically x is equal to the cube root of x plus 7, then plus 12. So the 12 is not underneath the root symbol. That's not true. That really should be a y. I'll fix that. To solve for y, I'd have to start by subtracting 12 from both sides. I then have to get rid of that cube root, which means I will cube both sides. On the left, I'm going to leave this simply as x minus 12 cubed, whereas on the right, that simplifies nicely where I can subtract 7 from both sides. X minus 12 cubed minus 7 is equal to y. This is the equation of my inverse. X minus 12 cubed minus 7. Okay, to find the inverse of this function, again, my original equation is y equals 1 over x plus 4. Therefore, the inverse is equal to x equals 1 over y plus 4. I'll subtract 4 from both sides. And here, I'm going to cross multiply. This y will go to this numerator, and this x minus 4 will go to this denominator. So that's y over 1 is equal to 1 over x minus 4. You can interchange the location of those two and those two parts of this equation. And this would be my final answer. This is really y is equal to this thing, since I don't need this 1 here. And that's my answer, 1 over x minus 4. My inverse equation is x is equal to 2 over y minus 4 plus 5. Solving this thing for y means I'd have to first subtract 5. And again, just like in the last problem, I can cross multiply. I'm going to multiply this y minus 4 here and put the x minus 5 down here. Now you could multiply this 2 down here, but it makes sense to leave it on this side of your equation. This means the y portion will be by itself. Y minus 4 over 1 is equal to 2 over x minus 5. This dividing by 1 is unnecessary, so I'll get rid of it. This is just y minus 4 is equal to 2 over x minus 5. And now I can add 4 to both sides, arriving at my final answer, 2 divided by x minus 5 plus 4. And that is the equation of my inverse. In questions 11 through 16, not each of these functions will have an inverse. So we have to look at the graphs to decide. If the function does have an inverse, we'll find it. Otherwise, we'll just move on. So here's the graph of x minus 4 squared plus 5. No surprise, that's the x squared function, which moved the vertex 4 places to the right and then up 5 places. And clearly, this thing does not have an inverse. You can choose any line that you would like to, but I'm seeing this one first. There's a horizontal line that goes through the graph 2 times. So this is not 1-to-1. That means there is no inverse on the domain of this function. In question 12, all that is different is the exponent is now a 3 instead of a 2, and it drastically changes the graph. Does this thing pass the horizontal line test? So let's see, all these horizontal lines are only going through the graph once. Same thing down here. Maybe there's a little issue here. It looks like it might be horizontal, but if you zoom in really close, the horizontal line here only meets the graph at one spot. So this thing is always increasing. A cubic function like this is definitely 1-to-1. So this thing has an inverse. So I'll just put, is this 1-to-1? And yes, it is. Therefore, I can rewrite this function as x is equal to y minus 4 cubed plus 5 and solve it for y. I'll subtract 5 from both sides. I'll take the cube root of both sides. And add 4. This equation is the inverse of the function that we started with. I knew one was going to exist because when I examined the graph, it was a 1-to-1 function. So here's the graph of the rational function in question 13. There's a vertical asymptote at -6, which makes sense. If I examine this graph, is it 1-to-1 is the question. 1-to-1. And if I look at it, okay, horizontal lines are only going through the graph once. There could be a question like here where it starts to get really level, but this thing, even though it's leveling off at what appears to be a horizontal asymptote of 3, this part of the graph is always dropping down just a little bit more every time, so it's never perfectly horizontal. And then the same thing happens on this side. It's always going up, so it's never level for more than 1 point. This means that every horizontal line that you draw goes through the graph once, so this yes passes the horizontal line test, meaning there is in fact an inverse. The inverse would be given by this equation, and it's our job to solve for y. I'll subtract 3 from both sides. And as we've seen, we can cross multiply in this problem. This can multiply up here, provided that this multiplies down here. These two parts are changing locations. In my next step, I'm not going to put this denominator of 1 because it is unnecessary in the problem. My equation becomes x plus 6 is equal to 1 over x minus 3, and I'm leaving off that division by 1. So to solve for y, I can subtract 6 from both sides. And this formula represents the equation of the inverse. Here's the graph for the equation in question 14. Again, asking the question, hey, is this 1 to 1? And definitely the answer is no. There's a lot of problems, but specifically if I focus on this one, I have a horizontal line that goes through the graph more than once, in fact 3 times. So no. On the domain of this function, which is all real numbers, the function is not 1 to 1, meaning it does not have an inverse. Same question for the graph in 15. Is this 1 to 1? I can already see that the answer is no. A lot of problems, but if you look at the value for y is equal to, that was supposed to be at 5, again, I have 2 points. So if you looked at the inverse, you would have 2 points lying on a vertical line, which means you couldn't, in fact, have a function. Said another way, there's no inverse for this equation. All right, so now we have the cube root of 1 minus x. Is this 1 to 1? I think it is. Seems like the answer is yes. Definitely every horizontal line is only going through the graph once, since this thing, as we head in this direction, is always moving upward, never becomes level, and then it always moves downward. So over here again, any horizontal line is only going to go through the graph once. Again, this function is kind of strange where at 1, it looks like it becomes vertical, but you never have one point that is above the other, so this is in fact a well-defined function. But all we need to know is that this thing definitely does have an inverse. So what is it? It's given by x is equal to the cube root of 1 minus y. I would have to cube both sides first to undo the cube root. And then I think I'll add y to both sides and then subtract x cubed. And this formula represents the inverse of the original equation. In question 17 and 18, something odd is going to happen within the problem. So to start with, we want to find the inverse of this function, and I know it exists because if you look at the graph of the square root of x minus 4, it definitely passes the horizontal line test. So this thing does, in fact, have an inverse. I want to note a couple of things first. This function has a domain, x values, that start at 4 and go to positive infinity. That's where the graph begins at x is equal to 4. And as the graph is moving in this direction, the x values start at 4 and move this way. So from 4 to infinity. Likewise, the range, the y values of this graph start at 0. And since the graph is moving upwards, you get all y values which start at 0 and go up forever. Therefore, the range of this function is from 0 to infinity. The thing to point out is that these are x's and these are y's. If you look at the inverse function, these two things should flip. All right, so let's do it. Let's find the inverse of this equation. The inverse is x is equal to the square root of y minus 4. And I already know what the domain and range of the inverse have to be. It's just the reverse of these two things. But anyways, to solve for y, I'm going to square both sides. Squaring the right side cancels the square root. I'm then going to add 4. And maybe I'll write it in this order, but here it is. Y is equal to x squared plus 4. That's the formula for my inverse. But there's something weird about this. If you graph this function, here it is at 4. It's a parabola, so it looks like this. But you actually also get some stuff over here too. You get the mirror image. So what's going on? I mean, this function, its inverse should be this thing, meaning it should be 1 to 1. But if you look at the entire graph and include all this stuff, well, it isn't 1 to 1. So how can we fix this? So like I said, the domain of this function is going to be the range of the graph that we started with. So the range up here, which are y values, become the domain down here because they are x values. Likewise, the range of this brand new inverse function should be the domain of the function that we started with. And the reason is, all these x values become y values down here. So this function is the inverse of this, provided that you look from 0 to infinity for the x values. That means you start here and you go this way and you just don't use any of these negative x values. So what I'll do is just erase them. This is the inverse. This equation is given by x squared plus 4, but what we do is get rid of this half of the graph. This will happen anytime we're dealing with some type of square root. It has an inverse. This is its equation, but we can't use the whole graph. We have to get rid of some of it, and it's either going to be the left side or the right side. And in this case, we got rid of the left side at 0 and took everything going to positive infinity. All right, let's find the inverse of y is equal to negative the square root of x with then plus 5 outside of the root symbol. And here's the graph of that function. Does it have an inverse? And the answer is yes, and because this is a 1-to-1 function, every horizontal line only goes through the graph once. But what I'm going to do to start with is just note that, okay, the domain of this function, the x values of it, start at 0 and go to positive infinity. Those are my x's. I begin at this point, 5 for y and 0 for x, and the graph moves in this direction, so my x values start here and go this way. Now the range, which represents my y values, okay, the largest y value is at 5, and since the graph is decreasing, that means I'm going from 5 down to minus infinity. The way we would write that in interval notation would be everything from negative infinity up to and including 5. So if you find the inverse of this function, its domain and range will flip. That means the domain of the inverse will be from negative infinity up to 5. So let's see what happens. This is my inverse. X is equal to negative the square root of y plus 5. If I want to solve for y, I would subtract 5 from both sides. And I'm going to square both sides. I'm going to put the step in here a little bit more carefully. I'm going to square the entire left and the entire right. I will leave the left side as x minus 5 squared, but when I square the right, squaring the negative just cancels it, and squaring the square root gives me y. And this, I'll reverse it, is the formula. It's y is equal to x minus 5 squared, just noting that that negative canceled when I squared both sides. But if you were to graph this function, x minus 5 squared is here, and it's a parabola that looks like, I'll draw that in here. Let's see. So it's here, and then it looks like this. Like this is my parabola. Something like that anyways. But that's just too much stuff. I do know that the domain of this inverse is going to be from negative infinity up to and including 5, and the range is from 0 to infinity. So what that means for us is I only want to take the part of the graph that starts here and goes backwards in this direction, meaning I want to erase all of this stuff here. So to fix this issue, along with just writing down the formula, I'll state the domain and note that on my graph, it simply just erases the left-hand side. I'm going to try to draw this in here just maybe a little bit more carefully, just so we have a better looking function. But it starts here and it increases up like this. That's the left side of the graph, x minus 5 squared. For question 19, I want to find the inverse of this function, so I'm telling you that it is one-to-one. We can do this. I'm just going to make a couple of notes about this equation. That is, do we know the vertical asymptote? Do we know the x-intercept? What about the y-intercept and the horizontal asymptote? We can get all of this information just by looking at this original equation. The vertical asymptote is x is equal to 2. That's the number that makes the denominator 0. The x-intercept is negative 5 comma 0, because if you put negative 5 in place of x, the numerator is 0. The y-intercept is 0 comma negative 5 halves. You can use a decimal of negative 2.5 if you'd like. And the ratio of the two numbers in front of the highest powered x terms is 1 over 1. So my horizontal asymptote is y equals 1. Anyway, let's figure out the inverse, which is x is equal to y plus 5 divided by y minus 2. I'm going to start by multiplying both sides by y minus 2. I'll then distribute the x. I think I'll add 2x to both sides and subtract y from both sides. I'll factor out y on the left side of my equation. And then my last step is to divide both sides by x plus 1, which takes me to my inverse. Y is equal to 2x plus 5, all divided by x minus 1. Well, if this equation represents the inverse of the function we started with, these four things should not be a surprise. Vertical asymptote, x-intercept, y-intercept, and then the horizontal asymptote. Well, the vertical asymptote, just by looking at the graph, is going to be x is equal to 1. And I say that as no surprise because if you go up here and put an x in place of this y, you precisely get that equation. X is equal to 1 instead of y is equal to 1. All right, now what about the x-intercept? That's the number that makes the numerator 0. That's negative 5 halves for x and 0 for y. And what do you know? If you look at the y-intercept, it'll become the x-intercept in this equation. This y becomes an x, and these two values trade places. The x becomes the y, and the y becomes the x. What about the y-intercept? If I look at my graph, it's the ratio of these two terms. That's 5 over negative 1. So that is 0, negative 5. No surprise again, because if you look here, the x-intercept will become the y-intercept. This x value becomes a y value, and the y value becomes an x value. Last thing would be the horizontal asymptote. In my equation, that's going to be 2 over 1, or simply y is equal to 2. But that makes sense. If you go up here and call this y, you get y equals 2 as one of the asymptotes. So here I took the equation, found the formula for its inverse, but everything trades places. X's become y's, and y's become x's everywhere, just like with domain and range back in question 17 and 18. Same idea in question 20, where I'd like to write down these four features of the graph and then find the inverse. So let's see, for the vertical asymptote, that would be x is equal to negative 5. The x-intercept appears to be 2 comma 0. The y-intercept is 0 for zero for x, and then negative 4/5 for y. And the horizontal asymptote is the ratio of the two numbers from the x terms, which is 2 over 1, or simply y is equal to 2. Anyway, my inverse is x is equal to 2 y minus 4 over y plus 5. Okay, I'll multiply both sides by y plus 5. And that's equal to 2y minus 4. I'll distribute the x. I will interchange the locations of the 5x and 2y terms. They'll both become negative, but we get x, y. We're subtracting 2y from both sides, and since we're also subtracting 5x, we get negative 5x minus 4. I can factor a y out on the left-hand side, and I get x minus 2. Well, I'm practically done. I just have to divide both sides by x minus 2, and here I have my inverse. And it should be, again, if we compare the vertical asymptote, x-intercept, y-intercept, and horizontal asymptote, they should match up with reversing the x's and y's with what appear up here. So let's see, vertical asymptote, oh, well, y equals 2 would have to become x equals 2. Okay, so that's good, x is equal to 2. Okay, the x-intercept, if I put on, I want to cancel this negative, so I need an extra negative. Cancel a 5 would mean I'd have to divide by 5 and multiply by 4. Okay, great. This means the x-intercept is definitely negative 4/5, 0. All right, now the y-intercept is going to be the ratio of these two terms, so that's 0, 2. And that matches up with switching out the x-intercept up here. The last thing is going to be my horizontal asymptote. It should be y is equal to negative 5. That's definitely the ratio of the two numbers in front of the x's, but it also comes from taking this x and calling it y. This is the formula of my inverse, and all of these match up with these terms here. For questions 21 through 24, this is merely just putting this equation into your graphing calculator and just making sure you understand what the graph looks like. So I typed in place of y1, again, you write that 3 caret x to get the exponent. And this is the picture you should see on your window. And maybe I'll just label a couple of points on here. So like if you make a table of values. You could do like maybe negative 1, 0, 1, and 2. If you put negative 1 into this function, that would give you 1/3. That makes sense. If you look at the graph, at negative 1, this y value is about 1/3 of the way down. If you put in 0, you should get 1, and that makes sense too. We get this point here. At 1, you get 3, and that's this value. That makes sense. And at 2, you get a value of 9, which is true. That's right here. So again, just understanding how to get a few points on the graph, but more importantly, plugging this into your graphing calculator just to make sure you're getting the same thing that I have. For each exponential function where you look at, the graph either increases or decreases. Here, the base, 1/3, is less than 1, which means your graph drops down like this. But it might be worthwhile just maybe for this example, coming up with a table of values. Maybe going negative 2, negative 1, 0, 1, and 2. It doesn't matter, just to get a few up here to make sure they match up with the graph I have on the right. The thing to point out is a negative exponent will flip the fraction, and then the 2 squares like you would normally square if it were positive 2. So if I put negative 2 into this function, the negative flips the fraction to 3/1, the 2 squares it, which gives you a value of 9. And that is precisely what is on the graph at negative 2 for x, positive 9. At negative 1, therefore, you should get positive 3. And that happens here. That's good. If you put 0 into the function, you should get 1 back. If you put in 1, you would get 1/3. And if you put in 2, you'd get 1/9. Here, there's no negative exponents, so the fraction doesn't flip. So you're just, in this case, squaring and raising the denominator to the first power. So you get 1/3 and then 1/9. All these numbers match up. Here at 0, you get 1. Then you get 1/3. Then you get about 1/9. And then it's disappearing. You can't really sketch these points any further. But this is the graph of 1/3 to the power of x. For the last two equations, I'm not going to make a table of values. It's easy enough just to get that from your graphing calculator, just maybe to describe that there's something different in this problem where there's a 5 now being multiplied to the whole function. If you ignore that 5, you have 0.5 to the x. I was expecting an exponential function that is decreasing, and certainly this one is. But notice at 0, it doesn't give you 1 back. In fact, it gives you 5. But this is no surprise. The 5 in front of my function just stretches the graph by multiplying each y value by 5. So the one that was at 1 goes to 5, and the rest stretch away as well. But as long as you just understand transformations and a basic exponential equation, this graph should really be no surprise. Okay, last one. Again, this is something you could put into your graphing calculator if you want to just try that out. It would be -2, but you want to have some parentheses around that 2 and then raise that to the x plus 1 power. That was kind of messy. Let me write that in here again. I would enter this as you put a negative, open parentheses, put a 2. You could either close the parentheses or you could also just put this as exponent and you want x plus 1, the whole thing to be in the exponent. This is how you enter this graph. But just to describe what this graph is doing, no surprise, the negative flips the graph over the x-axis. You're multiplying every single y value by -1. So instead of being up here, it's now down here. The other thing that happens is you have x plus 1 instead of just x within the exponent. That takes the whole graph and moves it one place to the left. So if you understand the graph of 2 to the x, you would take that graph, shift it one place to the left, and then flip it over the x-axis to arrive at this equation.